Our dynamic universe. The key areas covered will be Hubble's law showing the relationship between the recession velocity of a galaxy and its distance from us, and Hubble's law allowing us to estimate the age of the universe. What we will do today is use Hubble's law to calculate how far away a galaxy is, and describe how we can use Hubble's law to estimate the age of the universe. Hubble's law. The astronomer Edwin Hubble noticed in the 1920s that the light from some distant galaxies was shifted towards the red end of the spectrum. The size of the shift was the same for all elements coming from the galaxies. This shift was due to the galaxies moving away from Earth at speed.
Ever since Edwin Hubble discovered that the universe is expanding, there has been a great debate about the speed of this expansion, also called the Hubble constant. In 2000, scientists thought they had reached a consensus, with the Hubble constant at about 72. But since then, two methods of calculating the expansion rate have gotten farther and farther apart, and some scientists think it's too big of a difference to just be a statistical fluke. To calculate the Hubble constant, we need both a velocity and a distance. Velocities are easy. It requires measuring the redshift of a galaxy as it recedes. But distances are much harder. We need standard candles, objects that shine with an intrinsic brightness. That way, its observed brightness could be converted to a distance. The first method used to calculate the Hubble constant originated with Hubble himself. He started by measuring distances to nearby objects and working his way out, hence the name, the cosmic distance ladder. The first rung is within our Milky Way. Here we measure the distances to Cepheids, pulsating stars that have an intrinsic brightness. Then we look to nearby galaxies that contain both Cepheids and another type of standard candle, Type 1a supernovae. These exploding white dwarf stars also have an intrinsic brightness. After calibrating these supernovae, astronomers can then move out to a third rung, to even more distant galaxies that only contain supernovae. Linking all these measurements, a recent study has pinned the Hubble constant at 73. Instead of starting within our galaxy and looking out, the second method looks back in time to almost the beginning of the universe. Here we find the cosmic microwave background, the radiation left over from the Big Bang. The CMB's subtle variations in temperature describe changes in the density of the universe right after the Big Bang. Instead of standard candles, physicists use the size of the tiny fluctuations as standard yardsticks. With these yardsticks, they can calculate what the Hubble constant would be today. Recent estimates are at about 68, significantly lower than the cosmic distance ladder's approach. Both camps hope to resolve this debate in the coming years with the help of new telescopes and instruments. But if the discrepancy in the Hubble constant remains, it could mean that our understanding of the expansion of the universe is missing an ingredient. That something happened between the Big Bang and the present. Maybe there's a neutrino out there we haven't discovered. Maybe the mysterious force, dark energy, which makes up a significant portion of our universe, can change in strength. Or maybe subtle flaws in one or both approaches to the Hubble constant are giving us the wrong answer.
The bigger the shift, the faster the galaxy moves. Hubble found that the further away a galaxy was, the faster it was traveling. The relationship between the distance and speed of a galaxy is known as Hubble's law. V equals h0 multiplied by d, where h0 is Hubble's constant. This is 2.3 times 10 to the negative 18 per second. Using Hubble's constant. The units of Hubble's constant are per second, or 1 over time. The time found from 1 over h0 equals the age of the universe. The value of h0 has changed as measurements of the recessional velocity have become more accurate. Here's an activity to do. Find the age of the universe using Hubble's constant. If the units of Hubble's constant are per second, or 1 over time, then calculating the inverse of Hubble's constant should give us the age of the universe in seconds. So our h0 is 2.3 times 10 to the negative 18 per second. So 1 over h0 is 1 divided by this number. Putting that into a calculator, we get 4.35 times 10 to the 17 seconds. We now want to write this seconds in years. So we divide this by 60 times 24 times 365.25. That's how many seconds there are in a year. This comes out to approximately 13.78 billion years. Hubble's constant. The value of h0 equals 2.3 times 10 to the negative 18 per second is given in your data sheets and is the value you would use in an exam, but it can vary as more accurate measurements are made. The gradient of the line in the graph shown, this is speed versus distance of galaxies, provides a value for Hubble's constant. What is the speed of a galaxy relative to Earth that is at an approximate distance of 4.10 times 10 to the 23 meters from Earth? We want to use our Hubble's law equation, so that's V equals h0 d, and we can just fill in our values. So our h0 is 2.3 times 10 to the negative 18. Our distance is given in the question, that's 4.10 times 10 to the 23. And popping it into a calculator, we get V equals 9.43 times 10 to the power of 5 meters per second. So what is a light year? Sometimes distances can be given in light years. 1 light year is the distance travelled by light in 1 year. It can be calculated as follows using our speed distance time equation. Distance equals the speed of light times 1 year in seconds, and 1 year in seconds is 365 days times 24 hours times 60 minutes times 60 seconds. And so we're going to multiply the speed of light, this 3 times 10 to the 8, by our 1 year in seconds, and this comes out to be 9.46 times 10 to the power of 15 meters. This is 1 light year. The recessional velocity of a distant galaxy is 1.2 times 10 to the power of 7 meters per second. Show that the approximate distance to this galaxy is 5.2 times 10 to the 24 meters. So we need to show this number just here. We want to use our Hubble's law equation, so we've got V equals h0 d. We want to calculate the distance, and we've got our velocity, so 1.2 times 10 to the power of 7. That's going to be equal to Hubble's constant, so 2.3 times 10 to the negative 18, multiplied by our distance. We can rearrange this to give distance is velocity divided by Hubble's constant. This comes out as an answer of 5.2 times 10 to the 24. And that's in meters. Galaxies at different distances from the Earth have been found to have different speeds. The graph shows data for some distant galaxies. The graph is plotting speed against distance. A student studies this graph and makes the following statements. Which of these statements are correct? Let's take the statements one by one. Our first one says the speed of distant galaxies varies inversely with their distance from Earth. So we know that a graph showing an inverse relationship actually looks like this down here, and that's not what our graph looks like, so the first one is wrong. The gradient of the line gives the value of Hubble's constant. So the second one, this gradient here, this is a knowledge question. We know that the gradient of the line does give Hubble's constant. And the third point, the units for Hubble's constant is per second, and we know that to be correct. So 2 and 3 only, our answer is E. By observing the spectrum of light received from galaxy M101, astronomers have determined that the galaxy is moving away from us with a velocity of 5.5 times 10 to the 5 meters per second. Calculate the distance of the galaxy from us. So again, we want to use our Hubble's law equation. We've got V equals h0 d. We've been given the velocity, that's 5.5 times 10 to the 5. We know our Hubble's constant, that's 2.3 times 10 to the minus 18, and this is multiplied by d. Rearranging this gives our velocity divided by our Hubble's constant, which is 2.39 times 10 to the 23 meters.